Hello, everyone. This is Alice from Beijing. I'm so glad to see you on this iCANX-Talks again. I think every Friday we are met on this big platform. Last week we get the kick out for this opening. So many people ask me, Alice, what's iCANX-Talks? What's the X for? So now I might answer your questions. iCANX-Talks. The X is the question awaiting our answers. Without it, science could not support. X is unknown field, need our discovery. Without it, society couldn't go at once. X is a magic link among all human beings. Without it, emotion could not resonate. In iCANX talks, we believe each soul on this universe is a small universe. We believe communication between us while building the bridge for our small universe. We believe numberless small universes go together will converge a boundless universe, changing the present, creating the future, leading our human society into a new era. iCANX-Talks connect the world and the universe. Here is the answer for iCANX-Talks. Now I think everyone will love this platform because we want to connect the world and the universe upon connect everyone on this stage. We're building for the high tech. Last week, we invited two top scientists, John Rogers and Tony Huang, to deliver a talk for the latest achievement in the area. I think everyone heard that talk, all get excited. All know that all these top scientists are hard working, try to drive the world into a new area. Now this week, we got two scientists too, the top scientists. I mentioned the word is, the top one go to my mind is which one? You know that name. It's Zhonglin Wang. He's so famous for many years. Everyone think about, okay, Zhonglin. He's always on the top list for the world scientist. Now he invented so many things. Which one? I'm going to, give talk to you. And Zhonglin will give his latest achievement on a new area. This area has questions since 2,600 years ago. No one answered that question. No one knows the answers, but Zhonglin gets the answers. And Zhonglin now is going to tell you this magic story. And he's going to use this technology, to benefit the whole world, leading us to a new area. So now I'm going to invite Professor Zhonglin Wang to deliver his speech. Zhonglin, the word is yours. Please turn on your video and share your screen. Welcome.
First, I'd like to thank Alice for organizing this wonderful event, which used the most advanced technology. Let me share the screen to start share the screen. Second, I'll try to. Okay, share the screen.
Coming.
Yeah, it's coming.
Yeah, come here, Zhonglin. Time is yours. Yeah, okay. Ready to go.
Okay, I just make sure you can see the one. See the screen? Okay.
Yeah.
Okay. First, I'd like to thank Alice for organizing this special the events. Use the most advanced technology to tell the worldwide audience about the advances in many areas. And I'm very pleased to be here to share with many of you some of our research, because we believe good ideas, good progress belong to humankind. There's no boundary one way or the other. So today I'm just represent our team to talk about the topic, the origin of contact-electrification. How can this 2,600-year-old phenomenon contribute to energy in the future? So as you see here, this effect is well known. Everybody knows about it, and we knew it from a very long time ago, and you can see it happens everywhere, anywhere, all the time in our everyday life. So when you look at the history of the contact-electrification, it's very long. It's 300 BC, they have studied for this one, even up to recently. There's a recent review about this one. And people have different understanding. People say, some say this could be electron transfer, ion transfer, material species transfer, and it's not very conclusively until very recently. So this is a very old phenomenon. Everybody knows about it, and it touches every corner of our life. It happens for solid, liquid, even gas. So therefore, it's a very universal effect. So why do we are interested in this right now? This has been so old. Because first one, we need some new understanding. Second one, we have some new application about that. So let me go one by one. So when you look at this effect, if you look at the textbook for middle school, the first class when on top of electricity called electric charge. They say, well, hands touch the door panel, you get the electrostatic charge. We knew that. But why there's charge separation between one from the other one? Then the second one is about electric current. You say that there's a current delivered when you have a load and a voltage drop. So how come this electrostatic charge become current? So those are the two fundamental questions. I don't think they have very clear answers until very recently. And why do we interest this one? This go back to our study a few years ago for energy generation. As you can see, two dielectric medium contact, we have the contact electrification occurs, then the two electrons have electron exchange and back and forth, we have a AC current. As you see, this one, tap of this one give you some voltage current. And we made a lot of advance in this one, but this goes to phenomenon contact electrification. But why do we worry about this now? What's the advantage? We say this is a way to convert mechanical energy into electric power. But then you see, there's a way to do it. We have used this for decades and very powerful, which drive our world. So what's the advantage? As you can see, this is the triboelectric nano generator, and this is the comparison of the two. You can see this is the traditional electromagnetic generator, is T and G. And you can see this runs at a very low pace, but the output voltage is high. So if you compare theoretically in here at a low frequency, this is a very unique advantage, very good power output at low frequency. Then you say, why do we worry about low frequency, not high frequency? Because daily life is occupied low frequency, irregular. So whenever we start this work, 2011, and up to now, there's a lot of worldwide effort being devoted to this one. People use it for this one for micro nano power source, for flexible electronics, as well as fiber-based electronics. People also use it for cell power sensors, for MEMS, for robotics, and also machine and human interface, even biology. If you can extend this one to large area, you possibly could harvest this irregular wave energy from ocean, because the power output has reached by 500 watt per meter squares. The efficiency can reach 50%, even more. So this is what exciting. People want to look at this one, and my talk today is basically to present you these new things now. So what energy we try to solve? So we have plenty of energy which drive our society from a variety of corners, and we rely on this fossil energy, which is coal and oil. But as the world enters into the Internet of Things, mobile electronics, many things are moving. Many things need a portable power. That's the niche. We try to use the energy, harvest the environment to power those small electronics. That's the object of our research for the last 20 years. And what's for? You say, well, we have this powerful technology, energy storage, energy delivery, well established. But as the world advances, we have many new gadgets. We have more new gadgets than ever. We use it and monitor everything of our life. We want to track the speed, location, and whatever parameter we can measure, temperature and distribution pressure, everything. And this is the distributed energy. We're talking about that today, and how can we meet part of need as we moving forward. So this is the so-called big data. Where the big data come from? Come from the center network around, distributed around us. So what's the point? The point is that if you look at it from traditional energy, which is construct energy, to fix the size, that's the traditional way. But now all these things are moving, and also the power units, so the number is so huge, and their locations are unfixed. So from construct energy to distributed energy, from ordered application side to disordered, to wired to wireless. So this is similar like an entropy in electrochemistry. We to talk about energy distribution is like entropy, and this seems getting more and more numbers, more complicated. So we have no way to reduce a number one way or the other. That's where the world is moving towards too. So that's what we are working on, this energy harvesting from our environment to meet the needs for our future. So we work on this for a long time, from 1999 to today, of 20 years. And we raised this idea, soul power system. And this is the phrase I used in 2006 papers that up to date is very popular around the world. People call soul power system. The idea is utilize the energy around us. For example, a biological sensor, you can harvest the energy from biological system and power it and send the signal out. The power is not large, but you need it for sustainable operation. So they can, for solar power system, use the energy whenever it's available, wherever it's available. So this is the idea of solar power system. So when we first started, this was 2006, 2005, we used the zinc oxide nanowire, use the piezoelectric effect, use the EFM tip to trigger it and get a little power. And we call this nano generator because use nanowires and nano materials for energy conversion. And the way it work is around piezoelectric effect, and we call a nano generator for solar power system. Of course, that time the output is low, but as time advances, and this get a lot of enhancement in the last 2 decades or so. So this is called nano generator solar power system. So what's my talk today? First, I'd like to give some physics about contact-electrification, and then talk about the principle of traveling nano generator. So these two are answer the questions I posed when we look about what we wrote in middle school textbook, how the electrostatic charge create, how the flow. So let's look at the first question, the physics of contact-electrification. We know this effect for a long time, but there's a lot of different understanding. People from different angles say different things. So we make our TNG, trouble electric nano generator, into a box of a furnace box, so we can raise the temperature. And we find that by the temperature reach about 560 Kelvin, so the output of TNG drops almost to zero, which was a surprise for us back then. So we started at different temperature, the charge decay curve, and this decay behavior can be described using the Thermionic emission model for electrons. So we can quantify this curve, and we can use the model so-called electron Fermionic emission. This model is well established in physics. It's talk about if you have a barrier between metal and vacuum, if you raise the temperature, there's a possibility for electron to be escaped from the surface. As I say this one, apparently I'll tell you the charge transfer is due to the electron. We have many evidence to prove this one. I want to show you that just in the following slides. The first couple experiment we did was that we have an AFM tip, we have a dielectric. We can independently control the AFM tip temperature versus dielectric temperature. Then you can see fix the sample temperature, 330 Kelvin, raise the tip temperature from 313 to about 440. You can see the charge delivered to surfaces increases linearly. So why is so? If you use the band diagram for metal and dielectric, this is the metal and dielectric. This is the surface states of the dielectric. And normally below the Fermi level is occupied, but there's a little tail. Why this little tail? Is because the final temperature. This is called Fermi-Dirac function. So therefore, if these two meet, the the tail part is higher than unoccupied surface state, so electron beam kicking into dielectric. And you can manipulate the temperature between the tip and the sample, you can change the behavior. If you raise the tip temperature more, this tail become longer, so more electron kick into the dielectric. That's what you see experimentally here. So apparently, of this variation of temperatures, we found is electron is a dominant mechanism for charge transfer between dielectric, metal to dielectric. And we have more experiments to prove that. The other experiments that, okay, if you have a metal tip, you have dielectric, we can apply a bias. And this bias can change the Fermi level of the metal up or down, depend the bias applied. And we experiment, we find if you have zero bias, this is the charge you'd observed. If -2 volts, you get more charge. If you have 5 volts, you see the size of the charge even reverses. So again, this shows must be electron, because if you have ion, you cannot reverse the sign. So what is happening if you have a metal, dielectric, the surface states? If the two put in contact on occupied surface states being occupied electrons, so you have more electron kicking to the dielectric. Now, if you have a negative bias, which raise the Fermi level furthermore, more electron kick into the dielectric. That's what you see experimentally here. If you have a positive bias, you shift the Fermi level further down, then there's a possibility the occupied surface states of dielectric can be higher than metal, then electron can kick in here. That's what you see here. So this shows electron transfer is the dominant mechanism. Then the question, next quick answer. For this tip to develop electron to the surface, how close this tip has to be? An experiment, we can measure the phase of this harmonic tip and correlate with the charge delivered to the surface. We found only when the tip and the sample experience a repulsive force. So what is the repulsive force? Let me use the follow diagram to show you what do we mean. If you have a two interatomic, this is the interatomic potential here, and this is the equilibrium position, this is the bonding length. If you compress one atom against the other one, so you have the maximum electron cloud overlap. So only in this range, the charge transfer occurs. So this is called in the compressed region. If you go to a little away from equilibrium, this is called attractive region, there's no charge transfer occurs. So in reality, if you want to make one material transfer electron to the other one, you have to rub one against the other one so that it have a locally maximized electron cloud overlap. That's why you have trouble electricity. Trouble is involved in electrification, or contact electrification occurs. Why you have the contact? This is what it is. So we experiment find this one. Now, how do we explain this one? You can see that's the reality, what's happening, okay? So how do we explain this one over a general model? Because anything is made of atoms or molecules. So if this is the A atom of A materials, this is the B atom of B material. If they are separate too far away, the barrier of between the two are too high, no electron transfer from one to the other. However, if you compress one against the other one, the barrier height drops. Why? Let me use this animation to show you. This is the two interatomic potential. You have trapped electrons by each, okay? Then if press one against the other one, this is called tribology occurs. Then the barrier between the two lowered. There's a possibility for electron to transfer from here to there, so you have electron transfer. In such a case, charge transfer occurs, and if you separate, this charge will not flow back because it will have a lower energy. This remains negative charge, positive charge. Now, if you apply a temperature, the temperature apply activation energy, so the electron can be thermionically emitted, they recover itself. So this is a general model, so-called electron cloud overlap model for explain trouble electricity between two solids for a general case. Most recently, we found this thing not only occurs for dielectric, metal and dielectric, but also for semiconductor. So of course, semiconductor, but we found it interesting. So this is a P-type of semiconductor. sliding on the surface of the N semiconductor. And then you have an electrode here, you can measure the current flows when you slide this back and forth. Surprise, we see a DC current. A DC current is observed, not an AC current. So what is happening between the P and N is, besides they form a PN junction, is the dynamic variation of this front part, which can form new bonds when this move forward. When you form new bonds, each bond releases certain amount of energy. That energy serves like a quantum energy, excited electron hole pairs at the interface. The PN junction separate the holes, separate electrons from holes, so you see a DC current. This is called trouble voltaic effect. People can look at this, a few papers, understand this most recent advances of sliding one piece of semiconductor against the other one. So this is, again, this is still solid. But most interesting here is trouble electricity occurs for liquid too. You can see this for liquid. So you can see this is a bottle rubbed with paper, get surface charge here. Then you close to the pipe, you see the water be deflected. The water naturally have a charge. The water naturally have charge. This means what? Liquid and solid have contact-electrification. So how? Let me just show you. This liquid and solid have surface charge have been known for a very long time, which is known for the so-called electric double layer. So between solid and liquid, there's a layer of ions being absorbed on the surfaces and also distributed ions in the liquid. So therefore, you form this electric double layers. This is fundamentally important for many surfaces phenomena, catalysis, also the particle separation, biology, electrochemistry is very, very important phenomena. So you can have zeta potential, you can have a distribution here. So we recently studied this as well. Are these all ions? Are there any electron transfer between solid and liquid? So we tried probe this one from use the advanced techniques we are available right now. So this is the phenomenon occurs in our daily life, like ink, paint, the milk, everything have involved this electric double layer. So how do we do this one? So we have a surface, we drop a DA water on the surface. Then we wait the DA water to be dry, because when water contact the silica surface, they have charge transfer. And then what we did is wait the charge decay curve as a function of time at different temperatures. When you heat it up, of course, this after drop is dry. You can see this is 433 Kelvin, and this is 473. And at room temperature, it can be stay very long, hours be there. So this decay curve, most importantly, we initially surface apply a droplet. You measure surface charge, you jump over here. Then you wait it dry and heat up to 513 Kelvin for 10 minutes, it dropped to here. But it still have some residual charge. This is the ion remain on the surface. Then you apply a second drop, it rises to here. And then you dry it and heat up again, it dropped over here. Third, fourth, and you reach saturation. So this is the ion occupation on the surface. But at the very first step, you have electron and ion transfer. That's what is happening. So if you have a virgin surface at the very beginning, you have ion and electron transfer, which occurs at the very beginning. So how do we understand this one? Is just an analogy that means the total number of charge on the surface is fixed. Let me just like if you have 100 seats, all the seats number are fixed, but the first contact is electron occupy or ion occupy. The total number is same, like here is the number same. But when you heat up, only the ion remains, the electrons fermionic emitted. The second drop goes on, then you heat up, more ion sites be occupied, and because ion remain on the surface, electron be fermionic emitted. After several cycles, most of them are ion. So at the very beginning, have a virgin surface, electron transfer occurs. So this is going to change some bit about electric double layer understanding, and this we just devote some time to study this one more fundamentally. And this also depends on the pH. You have a pH 11 or pH 3, you can manipulate the sign of the charge on the surfaces. You can start the charge, build up multiple droplets, and all this can be manipulated. You can start the dynamics of the charge exchange between surfaces and a liquid versus electrons versus ions. Okay, so this is the liquid and solid case. So therefore, if you look at this furthermore, so if you have a virgin surface when a droplet liquid on the surface here, at the very beginning, besides ion absorption, it can be physical absorption or chemical absorption, but also can be electron transfer. So electron transfer can be here. So if you does not heat up, electron will remain there for some time. So basically, is have both type of charge on surfaces. And if you continue to do the experiment, just flow liquid, no heat up, the charge will remain as it was at the first droplet. And we measure the charge density. We found that interdistance between electrons is 16 nanometers. The distance between ions 30 nanometers. This is very sparsity on the surface. It's not very dense. Not very dense. Okay, so this is the revision to the electrical double layers. We have been familiar for decades, and hopefully I hope this brings something interesting. So how many charge on surfaces? One charge out of 10,000 surface atoms. That's roughly the number of how many charged the exchange on the surfaces. So what make things complicated used to be? It was trouble electricity and contact electrification convoluted. So this is the classical definition, what they call trouble electricity. Is two material contact, the charge transfer occurs. But now is that contact electrification is a quantum mechanical electron transfer process that occurs for any materials in any state, solid, liquid, gas, even at temperature up to 400 degrees C. Such effect is universal and is fundamentally unique in nature. In order to understand the contact electrification clearly, you have to separate tribology from contact electrification. If you put two together, it's called triboelectricity. That's cause the complications such as material species transfer. So this I try to ask the first question, how electrostatic charge get generated. Second question is how those electrostatic charge flow to give the current. If you look at the traditional way electromagnetic generator is the driving force, the Lorentz force drive electron flow in the metal rod. This is the power generator, very powerful. Now, if you look at Maxwell equations, there's a current called displacement current. You see, this is called conduction current. This is called displacement current. What is displacement current? Maxwell say displacement current is not electric current of moving charge, but a time-varying electric field. That's called a time-varying electric field. I use this one, he predicts the existence of the electromagnetic wave, he unified electricity and magnetism. But now this has to revise. Say how? Why do we need to revise this one? Is that if you have a piezoelectric material, you have surface charge if you apply a pressure. If you have a contact electrification, you have surface charge here. This can contribute this polarization as well. This polarization occurs even you have no electric field. You see, this term disappears if you have no electric field, but this happens at low frequency and add a term. So how do I understand this? Let me show you. This was the experiment. Piezoelectric materials are apply the pressure, you generate charge, and then this is where you generate current. So this is the medium polarization term. This is the displacement field. You substitute back here, get a permittivity by electric field, and this is the displacement current. This displacement current, that's predict electromagnetic wave. But now you need to include the contribution from the surface charge due to the piezoelectric effect. As you see here, you can see this the fingers move back and forth in the current. You need additional terms. So beside this term, you need additional term. This due to the piezoelectric effect as can derive the output power of our nano generator for the piezoelectric effect. But this idea can be extended. Then if you look at the classical textbook for electrodynamics, this is the medium polarization term which is built in Maxwell's equations here. Now, the the expressions that displacement field is proportional to electric field, the permittivity. If you have no electric field, there's no displacement current. However, if you have a trouble electricity, surface have charges, two material contact. So you need to add the contribution of this one to here. We need to modify this term. So how do we modify this one? And this was work we did in 2017. So this is the standard displacement vector. You need to add another term. This is the term due to the existence of the surface charge that are independent of presence of electric field. So if you change this one, you substitute Maxwell equations, you get a new equation. You get the modified Maxwell equations. This is the volume charge density, and this is the new displacement current have another term. So if you redefine the current and the charge density, you get the expanded Maxwell equations. But of course, this includes different terms here. These equations can be solved. You can differential equations. You can solve the integral equations. Let me show you some simplified solutions here. And you see this term, the term due to this one, give you the electromagnetic wave. This term give you the power output of electromagnetic generator. Both normally have very different frequencies, so they don't couple at our normal experiment. But in the future, if this one the high frequency, it could couple. So now we can separate them two, one from the other one. So you can look at the numerical calculation, this one, because I skip a lot here because this is very mathematical. The students can look at the paper, which I present the detailed solution of this one. But now let's look at you can solve this one numerically. You can calculate the power output of a nano generators as a function of different operation parameters, such as the load, such as the design parameters, distance between the plates, etc., which can be predicted precisely by the full solution. So we shall go to detail of this one. Let me just go more physics discussion here. So what's new here? You see the time derivative of magnetic field give you the fundamental electromagnetic generator. We know this one for decades, centuries. But now if you add another term, is the time variation of the polarization due to the surface polarization charge, such as trouble electricity. We give the maximum nano generator. So we can be piezoelectric effect, trouble electric effect. Inside the TNG is displacement current. Outside, go to load, is the capacitive current. The two meets at electrode, form a loop. That's what we see the current. So this is the driving force. Displacement current is driving force. The capacitive current is the output you see on the load. So why do we still call nano generator? Because when we first give this name, use nanowires to convert tiny little mechanical energy into electric power. But today's changes is nano generator is a field that uses displacement current as the driving force for effect convert mechanical energy to electric power. It doesn't matter use nanowire, nano or not, or nano material or not. So people should not just say, oh, nano, where's the nano? Well, it's a new physics field. It's advances as we understand furthermore into the field to this one. So it's a displacement current driven nano generator, which is different from this one. So if you look at the key difference here, the displacement current introduced Maxwell in 1861 and proposed the Maxwell equation later on predict the electromagnetic wave, which the theory of light, communication, everything. Now, if you add another term, you add the fundamental of the triboelectric piezoelectric nano generator, which can be for the energy. Both have very different frequencies. So they don't couple one with the other one. But who knows in the future? So if you use substitute this one back to here, you have the expanded Maxwell equations, which have an additional term here, which can solve sometime analytically and numerically. So you have two branches. This is the wave, this is the energy and the sensors. This is still a small field because look, we just work on it for the last 20 years or so. We need some time to build this one, and hopefully more people join this research can find new applications and exciting field which can help us solve some of the problem we are facing in the near future. So this is enough for the equations. And the next one was the figure of merits. Okay. For many people work on a solar cell, we have the efficiency to quantify the solar cell. Thermoelectric, we have the ZT factor. To optimize the ZT factor is the characteristic to describe performance of the thermoelectric material. So a few years ago, we asked our people, what is the factor for TNG? How do we quantify this one? And we have truly some outstanding postdoc and student. They work on this one. They study Carnot machines and compare the work, the output work is the voltage, integrate the charge. And then they work on this one, find the area of this VQ curve is the total energy output. So how do you maximize this one? Give you the maximum energy output. So we try to manipulate this one, see what's the best we can produce. So after some work, we derive the figure of merits. Figure of merits have two parts. The first part is materials figure of merits, is the surface charge density, square of the surface charge density. Then it's called the structure figure of merits, which is another term, which is what's dimension, is the contact separation mode, a sliding mode, or whatever mode here. Two put together is total figure of merits. So we do have a standard to measure this one. This number, we think we knew, right? No, we don't know that. If you look at the literature, they say, oh, we have a trouble series. We have wood is better than lead, lead is better than cotton. But by how much? Until very recently, there's no number be given because there's no standard measure this one. So we try to establish one, use the liquid metal as a common contact with the dielectric to measure the surface charge here. So with our good details, people can look at these papers to give the detail about this charge. And then you can see from here, we can move on. For example, standard equipment, methodology. After a few years effort, this is about 55 different polymer materials, we can quantify the surface charge for the first time. You can see one material is better than the other one by how much. Recently, we have been working on this one for 35 different oxide thin films. The paper is going to be published by Nature Communication in a couple of weeks. So you can see that very soon. So for the first time, we have a number for trouble electrification. This is the materials genome. We look at the material genome. This is another genome only be defined until very recently. So after I talk so much, maybe people ask me, for what? Just for fun? Just for interesting? Let me show you the application of TNG relying on contact electrification effect. So the following one you can see, if you use TNG to make this fiber base, this kind of tubular base, use carbon as the electrode, you make this one, you put in the shoes, a person walking can give you a small power, we can make those light flash. Light is a good way to illustrate. We do have power output, and which is sufficient to make some small electronics. If you have this flexible foldable electronics, you can see use this twist multiple run, you can have still give you output power. If you put an arm, you can see this have a sensors. You can sense different parts. The output is so high, you can register individual pixel. And you can use this one, a person free walking, you can give a couple of watts. But for some cases, it's enough, okay? Medical purposes, like a pacemaker, need a power source. How can we make it so power? Use the energy supplied by biological system. For example, our muscle motion. So this uses small rad, the small motions here. For a few years, we demonstrate we could potentially drive a similar pacemaker until last year. And our people have demonstrated for the large animal, they be able to drive commercial pacemaker for the first time. So this is a good advance. Use truly TNG as a power source for implantable medical devices. Anything you can think of, it can be a sensor too. So for medical purposes, it's a big area. Drug delivery. If you utilize the voltage generated, you can help the infiltration of drug into skins. Without use TNG, the drug infiltration is largely different. So if you put on these drugs on the skins, use patches here, the small power generated through physical motion can infiltrate the drug, deliver drug to some depth of the tissue. So this can be very interesting for medical purpose for that. Fibers, very common materials. Trouble electricity occurs also very often for fibers. So you can see use the fiber, you can make this one, the contact, you can use this one, make a rug, and this rug, press it, is a power source here. And this is what, this is the can be a sensor, you make a pixel, can be a sensor. You know, the advantage of this one is basically use the trouble electricity between fibers. We can design some of this one to more sophisticated application as well for you utilize these fibers, which is important for smart fabric or smart textile application here. So this trouble electricity is universal, is very good for these purposes. Because the TNG has a high output voltage, typically a few hundred to 1,000 volts, even more, you can make an electrostatic motor here. So you can use this drive a motor here. Let me show you this video here. And you can see, use a sliding TNG, can drive a small motor run at a rate of 1,300 rounds per minute, which is very good for some purposes. For the first demonstration, you can be an actuator, use the slow motion to convert to a fast-paced motion. You can also, the important thing, we talk about energy generation. People always ask me, so what about energy storage? Energy storage is very, very important for this one because our environment have irregular energy, fast pace, slow pace, irregular. We can convert this one to pulse as output. But now we need a regular output for electronic. So we need the power management circuits here. The power management circuits can rectify, manage this irregular power and storage it to make it useful. So this is, we need a very good system for this purpose. So this is called self-charging power unit, power generation, power management, and power storage and utilization. So therefore, we need each and every part of that to make the function. So this is this most recently make advances to this paper published Nano Energy, utilized for power management. You can see this one is the unit. They can make this really function here. You see this contact separation mode here, and then you can make a drop, have a output for purposes. So make it irregular energy to be regulated, to be constant output for some purposes here. And wind energy is everywhere, but effective utilization of wind energy is very difficult. In a lot of cases, very large size. So we use a fiber structure here. You see, this is a film. If you wind go here, this little tongue structure oscillates. You can see here a few years ago. You can see you blow air here, and you can make this one. So we can make this a few units. We can use one to make a solar power unit to detect chemical species in the environment, which can wireless transmission signal once every 10 to 20 minutes to a distance 1.5 kilometers away at a frequency 430 megahertz. So this is just the beginning. So I think that in the future, for solar powered environmental monitoring, fire protection, natural disaster prevention, anything, water quality tracking, we can utilize this solar powered system for many purposes. As here is a demonstration, use water flow, you can detect water quality and send a signal wireless to a central platform. You can collect the data, which shows that the interesting water quality mapping, which I think can be very useful for our environmental protection as well as natural disaster prevention. The second application is solar power sensors. You know, TNG is a technique that any physical motion gives you a signal. And this is a ping pong table. So we can make a ping pong table to detect the ball strike the edge of the surface to study the behavior of the players. And also we can start to test big data, the habit of a person. You can see each strike will give you an output voltage. So you can use this signal to detect the position of the ball struck it, even the velocity struck it, as well as the acceleration. So here it is. We make this ball. The ball hit the edge, the top edge or side edge, which can be different. So using this one can be a smart sensors can detect how the ball is. So you can use TAG for sports purposes. For many purposes, just a contact, a physical contact can give you some signals. This can be truly very interesting for any physical contact touch sensors here. So this could be, and this is the keyboard. We are all interested to use how can you identify the habit of a person who typing, because we are typing more things than we are writing a day. So we can use this keyboard here. You can see our people demonstrate, use the keyboard, you'll be able to demonstrate that, study the characteristic of different person, even a single finger touch 9 digits of this pads. If you study this characteristic for different characteristics derived here, you can identify who typed it, who typing. So this is just the beginning. Use this for individual identification of typing behavior identification. So I think this can be a very interesting topic to study human-machine interfacing, just like a sounds recognition. Medical, you can make this one small here, near ear, near the wrist here, and you can measure the pulses, also the blood pressure. We are more interested in measure blood pressure for people because the healthcare is very, very important for many people when it gets to a certain age. So can make it small enough so we can have a solar-powered healthcare kit for medical purposes. So this is we are trying to push this one. This is a ear hearing, because paper can make TNG. On the sonic wave tracking, you can record the sounds. You can record the sounds. You can tune the frequency range at which the sounds responses here. And let me show you. This is a recording system here. Okay, this is the first one. The recording. This is the natural music, the recording here. Then, if you play back, this is the playback. We preserve, we didn't do any data filtering. We preserve 90% of frequency and amplitude. Remember, this uses paper, 2 pieces of paper as a microphone to record this one. You can anyway communicate with robots. You can be a voice recorder here. I think this can be a TNG, can be a very popular thing. Because it's so diverse, you can literally choose anything you like. Power from wall droplet. The first time we demonstrate this wall droplet strike a dielectric surface get power was 2014. You can see this here. This is the shower head. Okay. When shower head sorry, this on the top here, TNG. Right. The principle here is use the contact electrification between water and liquid. And this recently draw a lot of interest from community because contact between liquid and solid. So this is a recent work. There's Professor Wang, Zhonglin Wang from CTU, and we published together. For this one, you can see use the wall droplet. You can largely improve the output to, you can see it's really significant. It's more power output than we thought. We believe it could be. So therefore, contact electrification with liquid and solid is very useful for this one. Many students do experiment. You have a YouTube shape here. If you change the contact area between the liquid and the YouTube, use the electrode here, you generate it. And if you shake this back, so when you handle liquid and solid, you never notice you have a charge generation. You probably never thought about that, but do remember when you shake a tube with a liquid side, there's a contact electrification occurs, which can change your catalysis behavior, change your other behaviors of chemistry. So I think this fundamentally can be very interesting for chemistry and biochemistry, and even chemical engineering. Okay. So water-driven electrochemical process. If you have many electrochemical process, well, you need power to drive it. So can we make this one? So this is put in the with use TNG. Without use TNG, you can, the corrosion rate is very different. So it can be an anti-corrosion device used to power half from the ocean. And this is the water treatment. You know, use the water flow energy, you can do the water treatment. And because we use catalysis only occurs on the surface of the sunlight, but what about deep water? But if you have a water flow, you can probably use to do water treatment at some depth. And use antibacterial and also antivirus. This is very key now. We have a lot of interest right now because we have this coronavirus, which is affect each of us. Can we use the energy from the environment as antibacterial, antivirus device here? Can we do that? So I think this can be a lot of opportunity for self-powered antivirus devices here. Blue energy. We talk about energy, say, well, how much you can generate? Oh, say we can generate about a watt, 100 milli or something. People say, well, this is small. Well, that's a small for small devices, but there's large power in the ocean. But to have such energy is extremely challenging because corrosion, depth of water, and difficult environment, very costly, very costly. Even we have 70 terawatts around the coast area, around global, but very little can be utilized. We cannot use that because of limitation of classic electromagnetic generators. Now, let's design a ball-shaped TNG. You can put a ball inside ball, and this ball can rock back and forth here. You can do this one by what? You can see this can be do this one, and the ball rolling back and forth, the contact-electrification can be changed. In such a case, you can have a power generation as well. So this random wobbling in any direction, this is just a simple demonstration. So how do you do that? So you say, well, disregard the depths, discard low frequency. We can make this a network. We can use in one maybe generate a time of but a lot of networking. This use computer simulation. We can generate a large power. So this is called a blue energy dream, which could be utilized for the future. So how do we improve? Well, materials is the key factor. You can see if you use a hard ball or soft ball. Hard ball and a soft ball, the output is dramatically different. So just change the softness of the ball, you can increase the output power by a factor of 4 to 5. So you can see each unit can give significant power. The key question, how do we integrate them together? So I think this can be a very interesting study topic in the near future, okay? The wave struck at low frequency, we can use a pendulum structure to make these things work for many cycles without stop. You can see this one, and you can see we put in this one, each cycle make this pendulum structure can last for 70, 80 seconds. And this can extend very long. I used this one recently, we achieved energy conversion efficiency of 28%. Just the power, use low frequency, we can convert low frequency to high frequency. How? You can use the light wind, generate powers, use our approach. So this is the called frequency amplification, use mechanical design. So fundamental, what's the advance? Electromagnetic generator use magnets, coils, the output is frequency squares. We use organic material, thin films, the output is linear to frequency. Both are different. Why? At low frequency, this have a big output than this one. So at low frequency, it's significant output voltage, make most power usable. But here, the electromagnetic generator, the output voltage is so low, most power you're unable to utilize it until you run a high pace. How much? About 4 and 5 hertz frequency, and this take over. So in our environment, if you have a high frequency, use the classical technology. You have low frequency, use TNG. So use complementary for the purpose of energy. Whatever environment you are interested in, you choose what you need. So we study in the lab. We try to see this in the water here. We can put this here. We can put the simulate what happens here. So hopefully one day we can utilize for ocean wave harvesting. Hopefully one day which can contribute to world energy at large. And this is a long goal and it's an ambitious goal. And so it can take quite a while to get there. But I think once we can do that, we have a solution for world energy at large. But of course, this do need a huge amount of work. Material scientists, chemists, mechanical engineering, and power management people, a lot of work to do this one. Okay, so where are the materials issue? We are all materials people. I have not talked about specific materials yet, but look at the Maxwell displacement current. This is the output of current of TNG. First one related to surface areas, surface structures. What's the surface areas best? Is too flat, not good. Too rough, not good. How rough is rough? So this is the first thing, surface nanostructure. Second one, surface charge density. How do we maximize surface charge density to max the power output? The third one, the permittivity. We use the dielectric materials to make surface permittivity, also robustness. Can we make this last longer? So all these parameters are constrained one with the other one. So we have a huge amount of material research to be done, remain to be done to make these things really viable for applications. So this opens a new field for material scientists, chemists to study organic materials for mechanical energy conversion, which we thought would be possible before. So let me give you a few flash because we do fundamental science, we do technology. What's the application? So we try to see what's the application. Where the market, this is the IDEX company evaluated for TNG from 2020 to 2040. They have billions of dollars on market for sensors. You can look at this report and read the details. And recently published for distributed generations. This includes solar cell, wind, everything. Have 300 billion market in 20 years or so. Huge demands, not only on the wired, concentrated, high quality energy, but also distributed irregular energy for many of things we are interested in. So therefore, there's a big need, but we have a long way to get there. But of course, we have a big, bright future. So a few years ago, we founded this company called Electron, and we make this air filter, make the masks here. And by surprise, we started this company 3 years ago. Until this year, we found it's a big application. And a lot of people need this mask for this antivirus protection. And our trouble-electric filter is ideal for these purposes. So this is the first things we commercialized a few years ago. And also, we all add this antibacterial, antivirus capability in our design. Hopefully, we can provide much better efficiency in the near future to help everybody so we can stay peace and healthy. Air filter, as you see, this central air has some problem nowadays. To run the central air, we can use this high voltage generated. We can do the air filtering for works, for office buildings, for houses, for many places you need. So this is the product for this one. We also do the haze removal for the automobile industry, and we do this already for 4 or 5 years. We run this one to multiple thousand, hundred thousand miles, and test if we below the particles below the standard, we could achieve that. The idea to utilize this is blow the air go through, generate high voltage absorb the particles so it can filter the air quality for this one. We're still looking for companies who are interested in this one, and hopefully we can commercialize this technology sometime soon. Shoes, we want to build these shoes, walking shoes, shoes which can generate power when you're walking. And we have this company called TNG data shoes here. And this company, we have a few our people, they are run this company. And then you can see this is the recently Flash they made for the term data twos. This is already commercialized or manufactured. This is live flashes on here. This is right here. We also used like this one, hopefully possibly the GPS positioning for the safety of kids and the healthcare of elder people in the near future. Okay. So for anybody interested, can look at this one. All right. So this is the one. Show the company. We also have the faculty who are interested in the public education, do this popular science, educate kids how they love science, how do they interest in science. This is both in English and in Chinese courses here. Utilize the TNG generator, use the trouble electric generator as the core technology, fabricate, manufacture a lot of this for popular science. It's called Maxwell's Innovation Popular Science Garden. Why do we call Maxwell? Because the TNG is driven by Maxwell displacement current. So we named it after his name, called Maxwell's Innovation Garden. Okay. So this, you can see some of the demonstration here, and this is the way demonstrate for energy breathing, energy of breathing. Let me see. Okay, and also for the hydrophobic surfaces, teaching kids how to love science. So this is have a lot of things for education purposes. Hopefully, a lot of kids will enjoy this program and love science and love engineering. So at the end, what I have been talking is our people's work. 20 years, mostly the work most done in the last 7-8 years. Our teamwork made a lot of contributions, and many people work with me. This is not the full list. As graduate students, postdoc scientists, visiting scientists, many of people contribute that, and also many of my colleagues and collaborate. Without them, I cannot do what I present to you at all. So I want to thank them for the outstanding contribution here. So here is the outlook. Today, I've mainly show you the science of contact-electrification, a 2,600 years problem, very old. There's no fiction older than 2,600 years old. This phenomenon is around us for 2,600 years old. Why we have not fully understand it? It's a forgotten corner by scientists. Why? Very simple. Because what's the use? Trouble electricity causes fire, causes damage. Why do we start it? Okay, the only thing useful is Xerox copy machine. So it's forgotten corner. But if you pick it up, it's fundamentally important. Solid and solid, solid and liquid, liquid and liquid. Many things we are interested in every day. We need in-depth understanding. So I think this is a very exciting thing to do. Then after you answer this one, how does electrostatic charge drive the current flow? That's Maxwell's displacement current. Maxwell's add a term in the Maxwell displacement current. We derive the equation for the nano generators, TNG. So you have the theory to work on. After you've done that, what's the application? What for what? Just for fun? Yes, a lot of fun as micro nano energy system, solar power sensors, large scale blue energy, even higher voltage. So this is we draw a so-called a roadmap. I hopefully in the next 10, 20 years we can achieve something like that. There's a video shot. This was January 1st of 2013. Just about a year after we published the first paper on TNG, and I was interviewed by CNN, and I present a big picture. So 7 years later, 8 years later, I think we made a lot of advance, and I think it makes sense. So persistency and consistency shows, but of course, we need a lot of young people to join the team to make this truly benefit to humankind, benefit to everyone.
Hello, Zhonglin.
Okay?
You finished?
Almost,
Okay.
because this video finished, I'm finished.
Okay, cool.
This was 7 years ago.
Dream come true.
Yeah.
Exciting. Okay, cool. Very nice. You look exactly the same as 7 years ago.
Okay. Let me mute this one.
Okay, cool.
Answer people's questions. So.
Okay, great. Okay, yeah, this is Professor Wang's, talk. Everyone listen
Okay,
to the talk,
very
you
good.
will understand why we're so excited.
Let me turn this off. Okay.
Sure. Okay. Yeah, so there are really, really many questions. We directly go to the question part, okay? Yeah,
Okay.
I'll put on the screen. The first one is from, South Island of New Zealand, Chimeric. Yeah, he's going to ask you for the, the work on the quantifying of the triple generator series and the surface charge density with different materials. Highly interesting. What effect can using a nanostructure surface have, and what are important features for the nanostructure surface and the limited of this approach? Okay.
Very good. Thank you for the question. When we first did the work, we used a flat surface. So if you have two material flat surface, but when you truly contact, it looks flat, but an atomic level is not flat. But you have to reach a level like a 2 angstrom or smaller to have the charge transfer. So only a part of that have charge transfer. So if you have too flat, it's no good. Then say we use the pyramid surface, we found the output power increase 20 times. So if you introduce the right surface nanostructure, you can enhance not only the contact area, but the charge density. It transports from one part to the other. But if you use too rough surfaces, it can have debris generated. So it cannot be too rough. So this remains a lot of work for us to do, because they say we manufacture nano surfaces, but not too rough. And so give us room to optimize.
Okay, great answers. Yeah, so the next question is from Peking University, Xu Chen. He's wondering for the commercialization. If eventually, go to as a commercialization device to power the IoT nodes, what do you think is the most critical problem now we're facing? We need to.
Like any technology, we always need better efficiency, smaller size, higher output power or power density, as well as high robustness. So we need to continue to improve the efficiency, the packaging technology, the robustness, as well as the output power. For example, I'm always asked by people say, can you power my cell phone? I said, well, there's a possibility. It depends the power need for that, depends how much power can generate. So I think if you consider lifetime of this technology, let's say first report 2012 January, up to now is 8 years, a little more than 8 years. The world have a lot of people interested in this one. And if you look at the solar cell and the lithium battery, they have been around for decades. People still have a lot of open question to answer to study for that. So I think with the short time for this one, I think we'll have good application very soon. So be open-minded, be persistent, and be excited and interesting. We're going to find something which probably surpass our expectation.
Yes, I do think so. I think we need, to keep on going for, trying all our best, to make it. Yeah, Professor Wang already done so many things and already, provided several kind of big devices to the commercialization. Yeah, so we are proud of that. We think we push forward. So the third question is from Shanghai Jiao Tong University, is a PhD student named Zhao Lin Chuan. He's asking for the blue energy. Yeah, it's a very interesting concept. I have a question about the application of a triple electrical net generator for blue energy. I'm curious about that microsurface structure could enhance the performance of these tanks, but it is sensitive to the humidity as well, which makes it not easily for the practical application. Besides, what's the key point to improve the performance of tanks in the future? Thank you very much.
Very good question. People always worry about the moisture effect. Definitely, there's a recent paper. If you have a moisture like 95%, TNG still works. Okay, but if you immerse this water, of course, it won't work. Anything you immerse in the water won't work, of course. So we need a packaging material. We need to fully package it. So that's why we did the ball shape. You fully package it, no water infiltration. So regardless whatever grow outside, it doesn't matter. But as long as no water infiltration, it should be okay. So that's why we need a new material for packaging. So to help this one last longer and stable.
Okay, so Dr. Wang, I want to, add in one, additional questions is for the blue energy. It was promoted, many years. So can you give us more words on that, how to, push all these kind of things to use for the wave of the ocean and to get eventually?
Okay, we proposed the idea in 2014, just a theoretical idea. Demonstrated the first work in 2015. So the idea, let me use this pen to illustrate to you, okay?
Yeah.
When a wave is slow pace, you can slow pace here, right? Slow pace, but that's too slow. So how do the wave strike once, and this pen oscillate multiple cycles? So we have a spring built in and resonance mechanism built in. So when a wave strikes once, this will oscillate for 80 seconds. Continue generate power. Then the next wave come in. This will be continue for another 80 seconds. If you continue on this one, we already achieved 28% efficiency of energy conversion. You think about it, 28%, how fast the field is. How much power is that? If you could do that, you find a fundamental solution to the world problem for energy over long term. And more importantly, this uses organic materials. Organic materials, this is lighter, cheaper, and also float on surfaces. Also sometimes anti-corrosion too. So therefore, you can make it really cheaper and better, and hopefully can be serve our purposes over a larger area. So I think this is just the beginning of the study of blue energy, and hopefully we have more people realize this one, and then we could realize something feasible in the near future.
Okay, great. We're looking for that. Yeah. So the next one is, hello, Professor Wang. I'm a Feng from Virginia Tech. I was wondering whether there is any effort to define the figure of merit for the fiber fabric, based terms, because the fiber varies in output, size, weight, stiffness, so far so on. It may be hard to compare the fibers intuitively. Okay.
Good question, because like you make a figure of merit for a solar cell. You have a solar panel. You make a figure of merit of the solar cell. It's a 1 meter square. The illumination is 1 kilowatt of light. How much efficient come? You have the standard to do that. But if you make a fiber-based one, the surface curvature is different. In that case, you can only measure the such like efficiency. We can only calibrate a material when its geometry is well defined. For example, what's the trouble electricity of this plastic? If you make a pen, well, it has a shape. which is very hard to say. But if I make a film, I can say, oh, I have a number for you. If I make a pen, the radius make a big difference. So therefore, if you want to define a figure of merit of the fabric, which is probably not a good flat surface to start with, use the flat surface materials, just like a material genome, you use the calibrated materials to set a standard so the worldwide people can compare your device is better than my device because your material is better.
Okay, it is. This is very important for the wearable, you know. Yeah, all this wearable device. Yeah, they're looking for all these things. So we go to the next question. Is hi, Professor Wang. My name is Zhonglin Chuan. Oh, I think I got this one. Should be, yeah, this one. Okay. Oh, sorry, I used the wrong button. Okay, yeah. Hello, Professor Wang. I'm Li Chunwu from University of Sheffield, UK. So considering the energy transformation, could I assume the upper limit of the terms output depends on the maximum surface charge of the materials, which means that initial electric storage in the materials? If not, what takes advantage in this amplitude of output, the velocity of these motions? Okay, thanks.
Very good. When you measure the efficiency, you need to fix out some parameters. Okay, for example, materials we use sigma square. Sigma square is just the square of the charge density. That one give you materials characterization. But now, if you have like a previous question, you have a fabric, you have a film, you have a ball, a pen, something like that. In such a case, we have a so-called two figure merits. One is materials. The second one is structure figure merits. So, is this structure or is this a structure? Both built in that equation. You need to figure out one and the other one. Both multiplied together is total figure merits. So you separate the structure figure merits from materials figure merits, then you can be more well defined.
Okay, great. I think that's, you know, a very good answers and very good questions. This time we'll have so many students from all over the world, you know. We'll have, and this time we have a question part from UK, Europe, and we have US, we have China. We also have someone from New Zealand. It's far away, but it is very active. We're proud of this iCAN-Talks, can go around the world, can get the people involved, get all these new informations and new technologies to go get abroad. So yeah, it is very, very proud of Zhonglin Wang. Actually, I mean, many of people was, you know, get excited by this talk, and many people was want to join this field. So, and here I try to use my own as examples, you know, why Zhonglin's talk was so moved to everyone. So this was a picture we took about 8 years ago, right, Zhonglin? Yeah, it's 2012.
June 2012, right?
Yeah, 2012 June. You know, which date? Can you recall that? It's 12. It's 12. Yeah, I remember it very clearly. It was in Italy. Yeah, so we joined the conference. It's a material congress, right? So we have lunch together. Did you remember what kind of question you asked me that time?
I forgot. I must say, your talk is wonderful.
Oh, thank you so much, Zhonglin. You are so encouraging. Yeah, you are so encouraging to everyone. So we sit next to each other, and this, you know, on these pictures was a scientist from Japan, scientist from Tsinghua University, Professor Li, Jingfeng. Yeah, so Zhonglin and me, we sit together for the lunch. So that time, Zhonglin asked me one question: Alice, what are you doing recently? You know, what about your research? I say I was doing for the energy, you know, harvesting. So Zhonglin said, oh, we have something new. We have something to show to your, energy harvesting. Yeah. So that time I don't believe what kind of is a triple electrical generator. I never heard of that. Yeah, I say I never heard of that. But Zhonglin sent me the papers, his personal publication on the nano energy. Remember, as the title is flexible triple, nano generator. And then he sent me that paper in the evening. I read it, and then next morning I was so excited. It's exactly I'm sleepless. I say so excited to see so many, wonderful results. Unbelievable. So I was get up, next morning very early, join my talk. I show the last slide is Zhonglin's new, publication. I say last night I read this paper, but the result is so good. It's too good to be believed. So once I came back to China, I asked my students, to try, see that possible we can do something in this. That's where we start. My triple electrical generator research. But it's gone so far, it's so exciting. Weeks later, I found out the result was so, exciting and so good. I sent an email to Zhonglin. Now I believe you. It really works. Yeah, it really works.
It works.
Yeah, it works. It really works. Works very well. So that gave me a big, impression. I think, I need to join the field, jump in the field as soon as possible. I need to try my best, to follow up. So that's my career change. That's the turning point of my career life, So Zhonglin, I want to show my, great kind of appreciation to you. I think many audience here, they want to share their appreciation to you because always your talk and your paper, your publication, all these things was, so encourageable to the young generation, to everyone in this field, or even they are not in this field. They got more, kind of emotions and kind of more encouragement from you. So I think that's a great, scientist. So you remember years ago, I wrote an article. Yeah, it was named 与王成王 in Chinese. So in English, it's greatness. That is greatness. Yeah, because I try to, tell everyone. So you need to, follow the greatest persons. Yeah, because they are doing so well. They try to get the people's, doing well. They try to help you. They try to, give you more kind of help in information. Try to check everyone out, from a whole, to the new futures, to bright futures. I think that's every time I met Zhonglin, when I listen to his talk, I even had some, conversations. He always, try to give you new ideas, kind of give you kind of new pictures, all these new things. So that's iCANX-Talks. I see here, I show this picture. I tell everyone the stories about, how I met Zhonglin. And I was, it's really, driven by Zhonglin because every day he was working so hard. He even sent your email, his latest result, at 12 o'clock in the evening. You see, that's our new paper. Alice, that's our new results. Oh my God, Zhonglin, I have you such a great friend. Yeah, I have need to, work very hard. I think this work is for everyone, even for the really young students, young researchers. Remember, follow the great scientist and to be great. That's the only way you can be great. I think, greatness, basically is greatness. It's my experience. And now should be everyone's, experience. Please follow up. See all these top scientists here. See what they are doing. So exciting. Yeah. So that's my, especially appreciation. And especially, stories share with everyone. So Zhonglin, now it's our great honors to give you a special certification in iCANX-Talks. Yeah.
You can send you hard copy or electronically.
Yeah, I will send you a hard copy. Okay. Yeah. After all this kind of difficulty time period, I will send it to you. Oh, yes, for sure. Everyone will have this hard copy. Firstly, the electrical, versions. Yeah, we do it online. So yeah, today everyone sees that this kind of lively show is a little bit different with others. You can see Zhonglin and me was in the same stage, within the same screen. Now I deliver all this honors from iCANX-Talks side to Zhonglin. You are the best scientist and you are leading the world. You high-tech was try to connect the world and the universe, everyone here, and you high-tech well to leading everyone into the new area. We follow up. Yeah, we try to, deliver this message to everyone. Zhonglin, that's all for you.
Thank
yeah,
you.
yeah.
Thank you very much, Alice. It's really a great honor, and like you and we have worked on this field. As the field advances, for example, we started the fundamental of contact-electrification. The more we do it, we find we didn't know this before. Even like this study of liquid and solid contact-electrification, we just started a year ago up to now, could have fundamental impact to chemistry, electrochemistry, and other things we are interested in. And I think the field can be broad. So we cover from chemistry to materials to physics and to mechanical engineering, electrical engineering, biomedical engineering, even environmental. So I think it's a broad field, and we need a lot of young people. They are they are talented, energetic, and exciting. Also willing to work hard. And I say nothing come easy. You have to work hard for it. But I think have a right direction is critically important. If you have a right direction, right platform, right field, if you work hard, you will definitely achieve something you yourself will not believe.
Okay, great. So we are right on time. Zhonglin, now we will have 5 minutes break. Next will come from our guest host is Tony Huang. Tony, 5 minutes later is your stage to introduce Xuanhe. Okay, now we have 5 minutes time. We come back at 9:30 on time. Okay, now we have a break. Zhonglin, thank you so much. You do so well. Yeah, you do so well. Great. Yeah.
Thanks very much.
Okay, yeah. So now we take a break. Yeah. So Tony, you still
even better than that last week. I think.
Oh, for sure. Yeah, you see, we have some kind of interesting thing. You never see this before. I mean, you see so many online shows, never see this. So next week, hey,
try exit and then re-enter.
Can you okay to attending that? No.
I still cannot open my video.